So in this case right here, right, what we're being asked to find is the electron affinity for chlorine, from the data right here for sodium chloride, and comparing those results to the published value that we have in those cases. So at the end of the day, right, all the reaction that we're really looking at is right the reaction of solid sodium plus gaseous chloride to form sodium chloride solid. Right, and it's always it's 1/2 equivalent, essentially. I mean, the technically correct way, right, is to do 2's, but in this case right here, right, we can just use a 1/2 coefficient in front of the chloride, right? So that's the reaction that we're looking at, is to figure out what those things are. Now, for all of this to happen, right, and I think Professor Rumsey went over this in class, right, is that you have to do a variety of different, you have to basically like add up a bunch of different reactions that will then end up forming what you actually are looking at right here, right? And so this is referred to as Hess's rule. You're going to learn about it much more in the thermochemistry part of the class, but this is important right now. So what you have to do. So when we're talking about ionization energies for atoms, right, we're talking about them actually in the gas phase. We're not talking about them as if they were the solid. So the first thing we have to do, right, is we have to do the sublimation, right, where we convert the sodium into gaseous sodium in that case. And so when we have gaseous sodium, right, then we can do the ionization, and that forms, Na plus in this case. And so then the same thing with the chlorine, right? So the chlorine is a gas, so that's perfectly fine, but it says chloride gas, right? So Cl2, so we have to break that apart. So the thing that we have to do here is that we have to break the bond energy in this case, to form an individual chlorine atom, right? And so now that we have individual chlorine atom, what we want to do now, right, is we want to convert that into Cl minus, and so that's going to be then our electron affinity, right? And that's the thing that we're trying to figure out, and that'll form Cl minus in this case. And so then the next thing that we want to do, right, is we want to form sodium chloride. We have our lattice energy, right, where the two of them come together, right, and then we have our delta HF, right, and so that's the heat of delta HF is this right here, right? Sorry, and then this right here is then the lattice energy, where the two of them come together. Now, the way that essentially all of the math works, right, for Hess's law is that we can add up all of these individual components right here, right, and those will have to equal the delta HF, right? So delta HF of this reaction, right, the formation of sodium chloride, is going to be equal to the delta H of sublimation, right, of sodium, right, so converting that into a gas, plus the ionization energy of sodium in this case, plus now we need to do, right, the bond breakage, right, and so the amount of bond energy that we have is 239 kilojoules per mole, right, and so that's how much you get. And so that this reaction right here is essentially Cl2 forming 2 Cls. In that case, we only need 1 Cl, so what we actually only need is half of the bond energy of Cl2 in that case. And that, again, right, is a thing where people get tripped up on when working on these things. Right, so we have that right there. And so then now, right, the ionization energy, the electron affinity, right, that's only for 1 chlorine atom. So we're back to just simply being that, right? So that's for chlorine. We have that. And then now the last thing, right, is the lattice energy of sodium chloride. We add all of those two together. So now the thing that we're trying to figure out, right, is what this value right here is. So all we have to do is just rearrange the whole system, right, and then basically subtract everything from it. So the electron affinity of chlorine is equal to the heat of formation of sodium chloride minus, and then it's just basically everything else that we had right there, right? So the delta H sublimation of sodium plus the ionization energy of sodium plus 1/2 the bond energy of Cl2 plus the lattice energy of sodium chloride, right? And that right there is the equation that we have to use. And all we have to do now is just plug in our values, right? So The only tricky part, right, is the conversion of. Yeah, sorry, give me a second. Why is it locked up? All right. Well, now the pen works, but now this part doesn't want to work. All right. Okay. I think we're back. Cool. Right. So all we have to do now is just simply plug in the values. So the only things, right, where we have to do where things are kind of off scale is that here, right, the ionization energy is given in electron volts, whereas everything else in kilojoules per mole. So we want to convert that. So if you remember back to a previous packet, let me just try and find it real quick. I gave the conversion. No, it's not this one. Was it the first week? Maybe it was the first week. Yeah, right. I gave the conversion of 1 electron volt into joules. And so, what we have to do that conversion, right, is essentially, right, we know that 60218 times 10 to the negative 19 joules per electron volt, right, is what we have for that. And then, right, and then this right here is essentially, per atom, so to say, right? When we're giving the ionization energy, it's typically per atom. And so what we want to do is we want to convert that into, per mole. And so for that, right, we just simply do 6.02 times 10 to the 23rd, right, per mole in that case, right? And that should give it to us in joules per mole. And then all we have to do then is just simply convert it, where we have 1 kilojoule is 1,000 joules. So if we do all of that, so we have 5.14 times 1.6021, 8 times 10 to the negative 19 times 6.02 times 10 to the 23rd divided by 1,000 gives us a value of 495.8, right? So I'll just say 496 kilojoules per mole. So now all of that's in the same scale. Right, and so now if I just simply plug in all of these numbers, right, so we have delta HF, which is, or sorry, the heat of formation for sodium chloride is negative 413 kilojoules per mole, minus delta H sublimation is 109 kilojoules per mole, plus the ionization energy, which we just calculated, which is 496 kilojoules per mole, plus chloride bond energy ratio, that's 239, so that's 1/2 of that. So 239 divided by 2 plus, right, and that's kilojoules per mole, plus the lattice energy, which is negative 789 kilojoules per mole. Right? We have all of that. Now we can just simply plug it into our calculator. Negative 413 minus 109 plus 496 plus 1/2 times 239 plus negative 289 gives us negative 348.5 kilojoules per mole, which is basically the same as the published value, right? Published value is negative 349, right? And so that's how you can essentially, right, use Hess's law, but also like use all this stuff with the lattice energies to figure all this stuff out, and get, you know, the values that you're looking for, that we have right here. Now, the second part of the question was, right, if we were to assume, you know, a scenario where sodium, you know, can have a 2+ charge, right? Right, and forms, you know, a stable lattice with chloride, right? What would, you know, all the energies in those cases be, right? How do you prove that that can't be the case, right? So the delta H of formation, right, is, you know, essentially shows us whether or not something can be formed or not, right? Or at least if it requires a lot of energy or something. And so what we're doing in this case right here, right? So if we're looking at this, right, we have sodium 2+ plus 2 chloride ions, right, to form, you know, sodium dichloride. We can just use the exact same approach that we had just done, whereas now the thing that we don't know is the delta HF, but we have all of the other values that we need. And so the difference here, though, is that for the sodium, right, to form this right here, so solid, gas, solid, in this case, right? So the sodium, right, has to first be converted into the gas phase. And then, right, it goes through the, you know, first ionization energy to form sodium plus. But then next, right, it has to go through a second ionization energy to form sodium 2+, right? So we're adding one more factor into that right there. Now, the next thing, right, that we can think about is that we have to, you know, if we're going through and we're doing the chloride, right, we're going to include the bond energy there, right, because that's going to break it. The difference is, right, we don't have to worry about dividing that by 2 because we're going to be forming 2 atoms of chloride, right? And that's what we need to form the final product, right? So we don't have to divide that by 2. However, the electron affinity, right, has to be multiplied by 2 in this case, right? So you have to have 2 of those to get, you know, 2, sorry, Cl minuses in this case. And so again, like, you just have to pay attention to what your ratios are for things and how all of that plays together. And so now that we have all of that right there, right, then this goes, and this is just simply going to be the lattice energy in this case. And that's going to be, you know, equal to the delta H of formation. So if we go through, right, and we do all of the you know, adding everything up, right, so the general equation is, right, that we have the delta H of formation of sodium dichloride is going to be equal to the delta H of sublimation for sodium, right? It's going to be equal to the first ionization energy of sodium. It'll also need the second ionization energy, right? So the ionization energy of Na+. In this case, it'll involve, you know, the bond breakage of Cl2, but now you're also going to need to have 2 of the electron affinities of Cl, right? And then you're also going to need to have the lattice energy in this case. And so for our instance, right, so as I said in the problem, you can just simply substitute in the lattice energy of magnesium chloride, right? It's kind of close. It's not 100% perfect, but, you know, it does its job to kind of prove the point that we're trying to make with this thing, right? Where, you know, the reason as to why the you know, formation of sodium dichloride doesn't exist. So if we go through and we throw in all of our numbers that we have from the previous part, right? So I'll just pull it up from here, so that way I don't have to, like, skip backwards. Right, so we have the delta H sublimation is 109 kilojoules per mole. Right, we have our first ionization energy, which I guess I should probably jump back, was 496 kilojoules per mole. Right, now I need that second ionization energy, so I give it again here in electron volts, so we can calculate what that is by just simply using, again, the same approach that we did previously. So I have 47.3 times 1.60218 times 10 to the negative 19 times 6.02 times 10 to the 23rd divided by 1,000 gives us a value of 4,562 kilojoules per mole. So very high. So 4,562 kilojoules per mole in this case for that. And so the next, right, the bond energy, so that is 239 kilojoules per mole plus 2 times the electron affinity value for chloride, or for chlorine, sorry. So I'm just going to use the published value of negative 349 kilojoules per mole plus the lattice energy that we're using, right, for the magnesium chloride. So that's negative 2,310 kilojoules per mole. So if I go in and I plug all these values in, right, so we have 109 plus 456 plus 4,562 plus 239 plus 2 times negative 349 plus negative 2,310. What we get is a heat of formation of 2,358 kilojoules per mole, right? So it's a positive value. So if you've taken any kind of thermo stuff, you should be familiar with the fact that delta H of formation that requires energy to be put in isn't going to necessarily happen on its own, right? There has to be a lot of energy that gets put into it, and it's probably not stable, right? Because it will just much rather just break apart and release that energy in those cases. And so that's right, how you can kind of prove that the formation of sodium dichloride is not favorable, right? And that's why it doesn't exist. And the big reason, right, it doesn't exist is that the ionization energy for that second step is huge. Right? We can do a different problem, right, where we look at the whole thing for magnesium, and you'll see then that the second ionization energy from going from magnesium plus to magnesium 2 plus is not as high. It's nowhere close to that, right? I think it's only like 700 kilojoules per mole. So very, very stable in that regard. But yeah, so that's how you do A3. And so